Hello, I am Qitao and this video is for my CEE534 term project. I do not have a webcam, so I put a picture of mine to show you what my face looks like. I'm from China and here's my Chinese name. The middle character Qi indicates my generation in the family and Tao means water wave in Chinese. As you may know, China is now facing a lot of pollution problems, and in this project, I will use Yuqiao Reservoir and Lin River as my targets to study the pollution patterns, and then I will use the knowledge we learned from this class to model those two patterns. If we go to Google Map, we can see the relative location of our targets with respect to the whole country. And if we zoom in, we can see the Tianjin city over here, which is very close to the capital Beijing. And the Yuqiao Reservoir is at the north side of Tianjin and provides drinking water to the city. Lin River is the upstream of the Yuqiao Reservoir, and if we go to Google satellite image, we can see that Lin River actually crosses a lot of villages and farmlands, and actually a lot of pollutants from those villages end up in the Lin River and finally goes to Yuqiao Reservoir. And the figure here shows the eutrophication problem of the reservoir. You can see at the entrance of Lin River, the problem is very serious. So in this study, the model I used was backward general explicit formulation. And since the channel of Lin River is made of concrete, it's assumed there's no permeability. I also assume that the contaminant discharged into the river has a first-order decay. Since the velocity of the flow in the river is high, we assume the case is advection dominated, so the dispersion coefficient E is very small in this case. Although the law enforcement agencies try to eradicate illegal industrial discharges into Lin River, there are still some small fertilizer factories operating during the night hours and closed during the daytime. Together with the sanitary discharges, the total injection of pollutants is not steady. So I changed the code for GX to simulate this discontinuous injection. All the concentration profiles on this slide are plotted at time step equals to 10,000. We can see that the edges here are very sharp. So when there is injection, the concentration jumps up, and when the injection is gone, the concentration goes to 0 immediately. Well, here is a plot for dx equals to 10 and dt equals to 1. And keeping the same dt value, I increase the dx from 10 to 50, and you can see the positions of the peaks are the same, but the edges are much smoother with larger dx. If we further increase dx to 100, it's even smoother with the same peak locations. Now, if we increase dt, please notice that with larger dt, the actual time will change, which is equals to 10,000 time steps times the dt value. When dt is changed from 1 to 5 by keeping the dx the same, you can see the peaks shifts to the right, and now we can only see 3 peaks here. If we further increase dt from 5 to 20, we can only see 1 peak here. And this makes sense because for larger dt, we're actually looking at a profile at longer time since we have the same time steps. And at the same time, the injections will flow with the river to downstream, and we also have the decay effects here. Now we will look at the concentration versus time plot. The injection point concentration is included as a reference, which is shown in the blue color here. And the red line is the station at x equals to 100,000 meters. And the green line is for 200,000 meter station. If we look into the graph at a specific time, we are actually looking at the concentration versus X profile at that time. And in the case of Lin River, surrounding villages do not have any drainage systems, so the sanitary wastewater is discharged into the Lin River without any treatment. So the sanitary pollution concentration in the river will also change with time, and a good method to distinguish the industrial pollution from the sanitary is to record the concentration profile while sending a lot of government agents to the field to make sure that none of those illegal factories are operating. And then at this time we can record the baseline, which is the pollution profile from sanitary use only. Later, if the monitored concentration at the gauge station is much higher than the baseline, it probably means that there are industrial sources discharging pollutants into the river. Another common phenomenon at Lin River is that the pollution sources are scattered instead of concentrated at only one point, so the MATLAB code is modified to simulate these multi-point discharge scenarios. A highlight for the result is that there can be a superposition between two discharge points if they are close to each other. Same as other natural rivers, Lin River does not have a constant channel width, so I also incorporated this change in my MATLAB code by expressing a lot of different parameters in the form of matrices. For this figure, the upstream width is still 50 meters, and if we narrow the downstream width from 50 to 5 meters, there will be a more propagation of the contaminants due to increased flow speed. And when the channel is widened at downstream from 50 meters to 100 or 200, you can see that the propagation becomes less at downstream. So in conclusion, we made a lot of assumptions when studying those water quality modeling formulations for the purpose of simplification. But in real life, we need to ask questions to those assumptions to produce a more reliable result. And this concludes my presentation today, and thank you for your attention. Thank you.